Good, good afternoon, sir.
Yes, good afternoon, Mother. Hello, Mother.
Yes, sir. Good afternoon, sir.
Mother, are you there?
Yes, sir. I'm here, sir. Can you hear me, sir?
Mother,
Yes, sir. Hello, sir.
Mother.
Sir, can you hear me?
Yes.
Can you hear me now? Oh, okay. Because I've been answering you since, but it seems you're not hearing me.
Hello, Mother.
Hello, sir. Can you hear me?
Where are others?
I have to like.
Where are others, Mother?
Excuse me, sir. I have to put it on our class group again.
Hello, Mother.
Hello, sir. I'm trying to like call my remaining classmates.
Where are others?
So I'm putting it on a class group. Like I'm not. I don't know. Like I'm not in control of their phones, so I'm just putting it on my class group again.
Oops. Hello, Imole. Ade Okuntobo. Okuntobo. Then.
Yes, sir. Sir?
Where are others?
Sir, I put it on the group. I don't know. Nobody's answering me, so I don't know what's going on.
I can't hear you at all.
I said I've put it on the class group, but nobody's answering. So I don't know. I don't know what's going on either.
Can you just type? Send me a message.
Okay, I'll send you a message.
So Prof will be joining us soon. Gentlemen, please be patient with us. Prof will join us very soon. Thank you. Yes, I'm coming. I'm coming. No, I have a class.
Hello? Hello? Good afternoon, all. Are you hearing me? Hello? Hello?
Hello, sir. Hello, sir. We are here, sir.
Are you hearing me?
Yes, sir. I can hear you, sir.
Tosin, are you online? Is the assistant lecturer online? Tosin, are you online?
I am online, sir. I'm replying you, sir. My name is.
Okay, yes, I can hear you now. I can see only one person online.
Hello, sir. I'm having issues with my network. I can't hear you, but
Okay, you cannot hear me, but I'm hearing you loud and clear. Hello? Okay, I have 11 people now. Now, is the class governor online? The class governor, if you are hearing me, unmute yourself and talk to me. Hello?
Hello, sir. Good afternoon.
Is the class governor online?
She's
Hello?
online, sir. She's online, sir. I don't know what's happening to her network. She's online, sir.
Okay.
Mole is online, sir.
I just want to be sure that everybody is part of this lecture.
Yes, sir. Everybody's around, sir.
Okay. Now, I'm going to share my screen. Hello, Tosi, if you are hearing me, you have disabled me from sharing my screen. Hello, Tosi. Hello, Tosi. Hello, Tosi. Hello, Tosi.
Yes, sir.
You have not allowed me to share my screen.
You can share now. You can share. I'm in the news now.
Eh?
I'm in the news. I mean, you can share, sir. You should be able to share.
I can do it now.
Yes. My student is having issues. I can't hear you. I can't hear you.
Okay, but you have allowed me to share my screen, Abby. Okay, yes, I can see now there's a difference. I can see there's a difference.
Okay.
Can everybody see my screen?
Yes, sir.
Can you see my screen?
Yes, sir.
I ask again, can you see my screen?
Yes, sir. Yes, sir. Yes.
Can you read to me what you are seeing here?
Application sequence of the ray tracing equation.
Okay, good. So we kick off with today's lecture. I will just make a reverse to where we stopped yesterday. And we'll just go from there to the end. The lecture may end this afternoon, or we can still meet for work examples and tests and all that. Now, we derived an equation for a line that goes between 2 points. If you can see my screen, a line that goes from point P naught to point P subscript A is a line segment, and we derived an equation for this line yesterday, which we stated as a parametric equation for a line in three-dimensional coordinate system. And the line equation goes like P, any point P on that line is an addition of the position vector of the starting point and a small portion of the length of that line, a small portion of the line segment. And that small portion is determined by the parameter T. You will recall that yesterday, we said if T was 0, P will be at the point P naught. And if T was 1, that arithmetic gave us T at point P, PA. That means that by varying the parameter T between 0 and 1, we could go through the length of that line segment. So this equation is a correct representation of that line. But let me remind you that all the elements in this equation, apart from parameter T, are position vectors. They are position vectors. The position vector at the beginning of the line, the position vector at the end of the line, and P is any position vector on that line. And the equation gives you the position vector P at any point on the line by specifying the value for T. So if you specify the value of T, which is on 5, then P naught will be the midpoint between P naught and P0. No, point P will be the midway between along that line segment. And if you specify the T to be 1/3, then of course, it will be a position vector that is 1/3 of the length of that line segment. So this equation is very important, and you need to make sure you understand it because we are going to apply it to solving problem of close range imaging that we have. Now, before we go to apply this equation, let us do some. Let us investigate some. Well, we worked some examples yesterday, and we can see work it. Now, this same equation was stated in terms of the coordinates of the point that are involved in that equation. And you will recollect that the XYZ of any point can be written in this alternative form, where we say XYZ equal XA, YA, ZA plus T times XB minus XA. That is for a line segment that goes between point A and point P sub T. We can write it in this Cartesian form where we express all the coordinates to do before. Now, what I actually am driving at is an example that we worked yesterday, whereby we are asked to find the equation of a line that goes from point 0, 1 to -2 and point 3, 4, 3. And we were asked to find that equation. It is on your lecture note. And let me let you know that this lecture note will be available to you immediately after this lecture. Now, we have that problem to find the equation of the line segment that goes from 0, 1, -2, that's the starting point, and 3, 4, and 3. These are in Cartesian coordinates. So writing them as vector, you have P equal A plus T times B minus A. And by putting the figures or the figures in the symbols, what you have in that equation is P equal 0, 1 minus 2, that's the starting point, plus a segment of that, a portion of that segment, a portion T of that segment, and the segment is of the length 3, 4, 3 minus 0, 1 minus 2. And that gives you the equation of the line as stated here. So which you will see when you get your own lecture note. Now, this is for a line segment that goes from point A to point B, and these are the equations. It's just a way of reminding ourselves what we learned before. Now, we have some examples that you are given a line that connects 2 points, coordinate 0, 9, 0, and coordinate 3, minus 1, minus 1, and minus 1 plus 1. These are position vectors. Find the equation of the line in Cartesian form and also in vector form. The vector form is given here, and the equation is just written as it is. Now, students always make some mistakes in the exam. They forget that P minus A is to subtract position vector A from position vector B, and then you get your equation. Sometimes they just put the value of the ending point here, and then that's subtract it. But notice that the line goes from A to B, and the equation should read P equal A, the starting point, plus a portion of the difference between the starting point and the ending point. B is the ending point. So you subtract A from B, get that segment, then the proportion T is left just there. Okay? Now, now we have the equation of a line said is in 2 parts: the starting point and a proportion of the segment, that is T times B minus A. But we said we can use this equation to manipulate that line in such a way that we can change its direction, we can change the size of the line, we can change the length of the line, we can also move the line physically to any point that we desire. Okay, those are called straight line transformation, where we change the line in any way we want. And the way we do it is, if we want to rotate the line, we will use a rotation equation to affect the line segment and not the starting point. Get that again. To translate a vector in any form, maybe by rotation, if it is a rotation transformation that we want to do for the line, multiply the difference. If it is a translation that we want to do, which does not the starting point, then just add the coordinate or the new translation, move the beginning of the line to any point that we want. Okay, so long as we don't affect the direction, the line will remain the same. But if you change the direction of the line, then you have changed the line. Okay, so the T into direction, that's the way you read it. So T multiply the direction, A is constant there, that's the beginning point. So if you want to move the line to add coordinate or subtract the line, but if you are trying to change the direction of the line, you have to multiply or use the matrix to multiply the direction. Now, let me also say that if you want to increase the length of the line, you have to multiply T by any number that you want. Okay, so that's what is done here, where you see that to translate this vector parallel to itself, T, you have to add the amount of parallel that you want to the starting point of the line and not to the direction. Okay. Now to make it a position, to make the vector a position vector, you have to subtract the starting point from itself. Then that thing will go to 0. The vector will now go to the origin and it becomes a position vector. So you can see that you can manipulate the vector in different ways to achieve different results. Note that these transformations are all done using matrix multiplication of vectors. I'm sure you have done that before in all your mathematics courses. But let's emphasize again. If you want to modify this line, if you want to turn, this is a line segment. This is a line equation for a line segment. If you want to change it to equation for a position vector, then you have to P naught, which is the starting point, you have to subtract the starting point from the vector expression, from the vector equation, and then the equation becomes P equal T times P naught, PA minus P naught. Then it becomes a position vector. But we normally work directly with a line vector or a line segment. So this equation will remain valid. Now, please take note. The line has a beginning point and a starting point. I mean, a beginning point and an ending point. Okay? You always subtract the beginning from the end to get the direction of the line, and then add it to the beginning to have the equation of the line. Now, we are going to go into the geometry of our single image photograph or single image photogrammetry. Then we'll be able to see how to apply this equation to every line on that geometry to be able to do certain calculations that we want to do. So look at this drawing. P naught is the starting point, P subscript A is the ending point, and the equation of the line, any point on this segment, P will be equal to P naught plus a small fraction T times PA minus P naught. Take note of that, okay? The origin is here. So it means that when there is origin there, every vector is a position vector. This P naught is a position vector, PA is a position vector, but PA minus P naught is a segment, not a position vector. We want to turn it to a position vector, then you have to move this origin to that place. And that's what we try to do when we transform. Now, you don't have to worry about this, it's just the derivation of the equation. Now, we want to turn that equation into a ray. Let me go back a little bit. The equation of the line is given as P equal P naught plus T into P naught minus P, or PA minus P naught. That's an error there. Now, if you want to turn this vector to a ray, what you have to do is to find the magnitude and direction of this ray. Okay, find the magnitude and direction, and of course, to convert a vector to a ray, just find the magnitude of the vector, use it to divide every element of the vector, then you have the ray. You have the ray, which is the direction vector. Now, that's what we try to do here. We try to find the length of PA minus P naught. Well, it doesn't affect it anyway. Now, this is the segment, the magnitude of the segment, length of the segment. And then we use to divide that equation. That gives us this expression. We're just dividing the vector, that equation, by the magnitude. So this is the magnitude. When you have it in either in single bar or double bar. Now, by letting T bar to be equal to the one on this side, and letting S to be equal to this, the equation of that line can change to a ray, then the projected equation can be written as an equation P equal P naught plus S times T, where T is given by that expression at the top here, and S is given by T over P naught minus PA. Recollect that we have not given any value to T. What we say is that T goes from 0 to 1. T goes from 0 to 1. Now, S is another one, which I will show you that the S can go from 0 to infinity. It can go from 0 to infinity. Why will it be like that? You can see, irrespective of what T is, the denominator, which is P naught minus PA, if this vector turns out to be a 0, then when you divide any number by 0, what do you get? What do you get? I'm talking to the class. When you divide a number by 0, what do you get? I'm talking to the class.
Infinity, sir.
You get infinity. So it means that if by any reason we have that denominator to be 0, the value of S, irrespective of the value of T, go to infinity. And if that value, P naught minus PA, becomes very large, S will become 0. Okay, so that means that S has a value that goes from 0 to infinity. But the important thing is that the equation of that line can now become P equal P naught plus S times T. What is important here is that T is now a unit vector along that segment, and S is the magnitude along that segment. So when you have a unit vector, which is the direction, that becomes a ray. It becomes a ray, and the ray has the property that it has a starting point P naught. Okay, it has a starting point P naught plus a scale times a direction. That is what the equation is. Now, this equation now is in form of a ray, okay, because it has a starting point, it has a scale, and it has a direction. Okay, so it is still the equation of the line, but has been put in a ray form. So this equation in ray form is the one that we are going to be using in our equation. And you have to realize how we arrive at this equation. So this equation, P equal P naught plus ST bar, is the same as the equation we had before, which is P into P naught, equal P naught plus T times P naught minus PA. So P naught minus PA is what and direction divided by the magnitude to get. So we just express this in direction form, and that, of course, will affect T and get the final equation of our line segment. Now have equation P equal P naught plus S times T. That means that if we know the S, then any length along that line we have the coordinate. Don't forget that P is also a position vector, any point along that the line segment. Now, note that the vector equation given here has a starting point position. You need to be able to understand that equation properly. Instead, note that the vector equation given here has a starting point position vector P naught and a direction vector T bar. So that means that and you are given the starting point, you are specifying find the coordinate of it. Quick corollaries, which will defined by two endpoints in a coordinate can be represented by the starting point and the direction, as you have seen now. Number two, corollary. Given the starting point and the direction of a line, it becomes a ray on which any point along it can be located in terms of coordinates and by specifying only the length along the line. So you can get any point in terms of coordinates by specifying, which is very advantageous. An example, given that a line connects 2 points, 0.090 and 0.3 minus 11, say find the equation of the line in vector form. And you don't have any problem with that because it's going to be 090 plus t into 3 minus 1 plus 1 minus 090. And that gives you the equation of the line. Number two, find the ray equivalent of this line. All you need to do is to find the magnitude and direction of the line segment, divide every element, then you have the equation of the ray. Now find the equation of a parallel line taken off from position 664. Just one, then the direction does not change. I'm talking to the class. Two parallel lines. They never meet because they
just that.
Sorry, I
I've
think
been using
Prof is
this
having
plan for
issues
8
with his
years.
network.
It has performed wonders for my efficiency, my health, and my happiness. It sounds
Am I being heard?
Yes, sir.
procedure that began with my troubled associates reciting all details of what had gone
My
wrong.
internet went off temporarily. Just came back now.
Okay, sir.
Now I have to reconnect my my page. Can you see my page?
Not yet, sir.
Tosi,
How this book was
Yes,
written
sir.
and why.
you have disallowed me.
I
Don't
was
try it
one
again,
of the
sir.
unhappiest lads in New York. I was selling
Okay, come back.
for a living. I didn't know what made a motor truck run. That wasn't all. I didn't want to know. I despised my job. I despised living in a cheap furnished room on West 56th Street, a room infested with
You can see. I can see it now. I can
I
see your
still
screen now.
remember that I had a
You can see my screen.
hanging
Yes,
on the
sir.
walls, and when I reached out in the morning to get a fresh necktie, the cockroaches scattered.
Okay. Now, assuming that you can still see my page, we have gone. Okay, so we were actually in the parametric equation of a ray. Okay, and we just looked at that example, which you can find the solution in that same page. Now, we are talking about the perspective projector as a ray. In other words, our perspective projector, that is the line, the projector is the line that connects the object point, the lens, the center of the lens, and the image point together. It is called a projector. And because all the lines converge at a point, we always refer to them as perspective projector. But each one is a ray. The perspective projector is the straight line from the object point passing through the projection center and forming a point on the image. We are going to show an example of that. Okay. Now, this is the point where we are. I need to move this one away so that it does not obstruct what you're seeing. Now, we have our perspective projector. Okay, we have our perspective projector. As you can see from this geometry, which we have treated several times, you will see that the object point A, for example, there is a line that takes off from that point. It goes through the perspective center of the lens, and then, thank you. Now, it goes through the perspective center of the lens, and then forms the image at the small a, at the point small a on the image, okay, on the image. So that is a projector, and it goes from point A, big A on the object, to point O on the lens, and then back to point A, small a on the image. It's the same straight line, but in two different segments. That means that every projector has two segments. The segment from the object to the center of the lens of the camera, and the segment from the camera to the image point A. I take that again. Every projector in this single image geometry has two segments, which are in the same direction. The segment that goes from A to O, which is the center of the lens of the camera, and then the segment that goes from the camera to form the image on A, and they are in the same direction. That is what we call the collinearity condition. Collinearity condition. So every projector obeys the collinearity condition, where the two segments, segment from the object to the lens, and the segment from the lens to the object, they are along the same direction, same straight line. Okay, so now, if we form an equation, a ray equation, which we have discussed before, we form for the segment of the line that goes from the object to the center of the lens. We can also form a ray which will have been in the same direction from the center of the lens to the image point on the image. And they will have the same direction. So they have the same direction. That means that they belong to the same ray, and they only differ by the scale factor. By the scale factor. Now, the position vector from the projections, that's object space position, which we have seen in that image. That is from point A to the projection center. Said the position vector from the projection center to the object point, that's the object space position vector. Both lines can be represented as rays, as we have discussed in the section on ray analysis. And since they have the same starting point at the projection center and direction, but only differ in scale, in the scale factor, they are called coincident or collinear rays. And that is what you call the collinearity condition. So when I ask you what is the collinearity condition, you will say that collinearity condition is that the ray from the object to the camera and the ray from the camera to the image, they all are along the same line. They have the same direction and they have the same starting point. Okay. Now let's go ahead again. Now, analytic geometry approach to restitution. Now, what we are going to do is we'll now assume that there is a ray equation that can be written for the segment from O to A, and then another ray equation from O to small a. But they have the same direction, and by measuring coordinates of that point on the image and turning it into a virtual 3D system, you can compute the direction of that line, as we are going to see. So since from O to big A has the same direction as from O to small a, then the ray equations will be the same, except for the scale. And you will see what will happen now. Let's take an example. The mathematical transformation from the ground point to photo coordinate can be established under the assumption of collinearity. In the exam, if I ask you, explain what you mean by collinearity. So collinearity means that the ray that is from the object to the camera lens and that from the camera to the image, they're all on the same line and they have the same direction. Okay. Now, no, we have gone beyond this one. My internet again. Okay. We have formed our image model. Now, we have brought our geometry. I hope you are seeing me and you are hearing me. Can you indicate that you are hearing me? Because we are at a critical point.
We are hearing you, sir.
We can hear you, sir.
Now, this page is very important. If you have been sleeping before, somebody is playing radio on this line. Don't play your radio on this line.
You won't find anything new.
Don't tune your radio on this line. Now, if you have been sleeping before, don't sleep. This page is very important. Now, the projector equation, the ray equation that we derived before, we can now apply it to the geometry of the single image photography that we have taken. Now, the perspective projector is a ray from the object through the projection center to the image plane. It will be represented as a ray under two assumptions. Number one assumption, when the image is horizontal and not tilted in any way, then there is no rotation to it. And that is the condition that you will use in your practical when you level your instrument, your tripod, and put your camera on it, or you level your tripod and put your theodolite. Now, this equation becomes, the ray equation becomes T equal P naught plus S times T. Okay? Now, we're assuming a situation where the two rays originate from the same point, that's from the same principal point, which is this point on the image. Can you look at this drawing? So they are all originating from that single point. and it's the same ray that goes to the point A, and the same ray that goes to the object. The object is at the point big A. This is big A on the ground. This is small a on the image, and you can see that it's a straight line. Okay, this is to make it clearer what we are saying. Now, when we assume that the starting point is at this projection center, that's the center of the lens, then you find that our P naught goes to 0, right? It has value 0, 0, 0. That is now the origin of our ray. And then because that goes to 0, our ray now becomes S times T, small s times T. T is the direction of that line. Yeah? T is the direction of that line. Now, the object space segment also have the equation P equal P naught plus big S times T. Okay, big S times T. Since the origin here and there, the two rays are starting from the same point, then this also becomes become S times T. Okay, now that's the assumption that the two rays are from the same. Not interested in the, we're not interested in the T. When the R is an identity here. When the image or when the origin is not 0, right? When the origin is not 0, P naught and P naught they remain. R is identity, so the expression will become P equal P naught plus small s T for the image section from O to small a, and then the big one, P, the same P, is P naught plus big S T. That's what we're going to have. And let's see how this turns out. Please take note of this point. We note here that the image space ray can be completely determined by measurement of image coordinates. And I show that again. This ray here from O to small a, the direction of it can be determined by measuring the coordinate of this point on the image plane. So when you get your image, measure the coordinate of a point, okay? And then that can be used to determine the direction of this line, as we are going to see. Once the coordinates are measured, then the direction of that line is established. And since it is the same direction with the ray that goes to the object, okay, so we can use that direction as the direction for this other one, and then what will be missing will be the expression for scale in both cases. Now, this ray equation is significant in image metrology because the direction of each ray can be established by measuring the image coordinates of the point. And since the ray has the projection center and starting point, this ray equation can be used to compute coordinates of at given distances from the camera along the ray. Note that the direction of the ray can be generated from measured image coordinates. Now, the point here is any object space ray has a length whose value is known, but can be estimated by taking the average distance from the camera position to the object location in addition to the measured image coordinates. This is called ray tracing. This is called ray tracing. So you retrace when you are able to use that ray, you trace it to a point where you can use it to compute the coordinate of any point on the ground. You have to do ray tracing. Any of the ray equations can be decomposed to derive a pair of equations which may be used for computations of unknown object position. These are just precautions. In this process, measured image space coordinates are used to define the array for each point on the image. The problem then is to solve, it will be solved in two stages. One, define the array in the virtual image space. Two, define the array in the object space. These two arrays have the same origin and the same direction, but have different scale factors, which must be determined in order to employ this method in the construction process. Now, by measuring the coordinate of the image small x, small y, that small x, small y, you use it to compute the direction of the image space section. That direction is borrowed to compute the direction of the big object point. And then with the scale that we are going to, I will show you how to determine the scale now. You can compute the coordinate of the ground point A. That is the method you are going to use. Now, let us take some assumptions. Assumption number one, the optical axis of your camera when you are taking your picture will be horizontal and leveled, that is no tilt. In other words, you have to level your tripod or level your hand. If your camera is held in your hand, if it is on a tripod, you have to make sure the tripod is horizontal. And if it is in your hand, you have to steady your hand and hold the camera so that the optical axis of that camera is horizontal. Okay, is horizontal. Number two, axis of the camera is perpendicular. To take an object, the object has to be in your front. Your camera in a way that the optical axis is perpendicular to the face of the object you are taking. Number three, the distance of camera from the object, which we denote here as D, is either known or measured. So in other words, complete information will be taken, not just take the image and run away. You have to take the image and also measure the approximate distance from the camera position to the face of the object. And of course, since the optical axis is perpendicular to the face of the object, then that distance is the length of the perpendicular, or the length of the optical axis. Number four, the camera position P0 is also known. The position where your camera is, you have to know it in terms of the coordinate system. So you either stand on a pillar or you determine the coordinate of where the camera will be in order to put the camera there so that you know the P0. That's the starting point of all your rays. Number five, by measuring image coordinates, the ray equations can be written as follows. The image space ray is written as P equal P0 plus SRT. Our rotation is not available because we have leveled the instrument, so there's no rotation. That rotation becomes an identity matrix. So your formula becomes P equal P0 plus S small st. Now the corresponding object space ray becomes P equal RT. This T can be determined for, okay? And then once you do that, you come here, the T is available for this equation. And once the scale is known, then this you can get this point P will now be the object location, which on the drawing on the left side will show you the coordinate of this point, A will be computed. Now, before we go, the other dimension that I need to let you know is that the y-axis of the image is going from down to up on this page. Y-axis is from down to up. X-axis is from left to right. And the Z-axis is your punching axis that is going from back to front. When you have a situation where the two axes of the image are interchanged, then it becomes a left-handed system. Becomes a left-handed system. The object space is always right-handed in our surveying parlance. Object space is always right-handed. And the right-handed system is one in which your index finger points in the X direction, then the lower finger points, the middle finger points in the Y direction, then the Z axis points in the direction of the thumb. That is a right-handed coordinate system. And that is the coordinate system we use in our GPS, in our ground surveying method, and for defining our object space. For the image space, by virtue of the camera that we use, whose Z-axis is always along the line of sight, then the image system has a left-handed system. It has a left-handed coordinate system. So because of the differences in the right-handed, because our object is in the right-handed system, our image is in the left-handed system. So we have to change when we are doing calculation. All our calculations are done inside the image left-handed system. So the object coordinate that you have to convert them from a right-handed system to a left-handed system to do your calculation inside the image, and then you come back and turn them, the result is now turned back into a right-handed system. And that's what they call object swapping, object coordinate swapping. So you have to swap the coordinate of the object when you want to do your calculation. And when you are finished, the result will have to be turned back into the right-handed. You have to swap it back to the right-handed system. Now, we'll go into an example. Application sequence of the single ray tracing equation. We are almost at the end of the lecture. To apply this ray tracing concept to single image processing, we proceed as follows. Don't forget that on the previous page, you have the assumptions, okay? And the only assumption that is missing here is that object swapping has to be done. In other words, you have to swap the object, and the swapping of the object involves you change the Z-axis back to Y-axis and Y-axis to Z-axis by just interchanging the coordinate. That's what we do, but there's an expression that we use for that. Now, the sequence of applying this method is to apply this ray tracing concept to single image processing. We proceed as follows. 1, specify camera parameters. That is the focal length. F, the camera position at time of imaging, P0. Camera distance, H. Call it D here, not H. Camera distance, D or H from object, which I mentioned before. Number 2, identify and measure coordinates of a point P on the image, XA and YA. Number 3, generate image position vector, P, as a virtual coordinate system where you have XA, YA, which you've measured. You augment that with F, the focal length, and it becomes a virtual 3D vector. Virtual 3D vector. Now, number 4, compute the magnitude and direction of the image vector as follows. S, using Pythagoras theorem, is XA squared plus YA squared plus F squared. Now, You can now convert the image space vector into a direction vector by dividing every element of that image vector by the magnitude. The magnitude that we have computed is named small s. That is the small s, that is the length of the image, okay, in the image itself. Now the direction vector, now express it dx, dy, dz, and the expression is divide x by that magnitude, divide the y by the magnitude, and f by the magnitude. You have gotten the image space direction vector. You have gotten the image space direction vector. Now, since the image space direction, image space ray and the object space ray are in the same direction by collinearity, they are collinear and they have the same direction. Two lines that are running parallel have the same direction and they can never cross themselves. So when they are coincident, they are running along the same line and they have the same direction. Now, two things we have gotten from here now. We have gotten the small s for the image scale, and we have gotten the direction. Now, let's go to number 5 item. The object space ray equation may now be written as assuming R is identity, which we have taken care of by making sure that we use the normal case. The image space equation can now be, we plug all this information into the equation that we had before, which is the equation on the last line here, with R being identity. That's the equation on the last line here. We plug all those values. We have T, we have T, we have R to be 1. S is the big S, which we have left. So let's plug what we know from the image into this equation. And that's what we have at this point. So that equation becomes P equal P naught plus S over F times D. Now, how did we get this? How did we get S over D? We'll see as time goes on. Now, D is the distance that we measured from the field. D is the average distance at which you are standing before the object which you are imaging with your camera. So that D is the distance. Now, our S, our big S is divided by F. Now, we get this big S from expressing this equation of this line in terms of X, Y, Z. I mean, in terms of the Cartesian form. When we express it in Cartesian form, this last element is always the image scale. That's always the image scale. Okay, when you express it this way, is the image scale, and that's what we use here to get the image scale, and the distance that we measure from the object scale is so that we know the length of the total length of the object, and that expression gives us this expression small s over f times d will give us the image space scale, which is s times t. Let's take note that big S, this is big S. The small s that we have there, we have used it to compute. Now, this last expression, another advantage of this method is that you can get this image space scale. And when you get the image space scale, you multiply that scale by D, what you get is the big scale for the object point. Now, where P naught is the camera position. Now, let's go ahead. Now, this is only trying to buttress our point. Now, to apply this ray tracing concept to single image, we proceed also, I think we have passed, this is a repetition. This is a repetition. Oh yeah, that's a repetition. Yeah, which leads us to the same point. So we need to check that. I'll remove it. Now, we have an example application of this equation so that will make us to understand what equation does. Now, the example says a single image was taken of the front face. Take note of that. A single image was taken. Mm. The image of a corner point on the image of a corner point on the roof has image coordinates and was 45 mm and 48 mm. That's XA and YA. Given that the camera was located 50 meters from the house, that's our big D. Compute the height of the point from the and at the height of 1.2 meters. That means
Sorry, I think Prof has issues with his connection once again. We should join us soon. We are almost towards the end of the class.
hello, are you hearing me?
Yes, sir, we can hear you, sir.
Hello. My internet went off. Can you see my page?
Yes,
I can
sir.
see it. You can see it.
Great. My internet is having problem.
We can see your page, sir.
Okay, you can see my page. Now, this was the question that the example that we were working on. And so let's see the solution. Make sure you understand the problem. This problem is similar to what you do in the film. A single image was taken of the front face of a building with a camera whose focal length is 100 mm. The image of a corner point on the roof has image coordinates -45, X is -45 mm, Y is 48 mm. Given that the camera was located 50 meters from the house, compute the height of the point from the ground. The camera position at the time of imaging is 100 meters X or easting, 0 meter northing, and 1.2 meter height. Now, method of solution. Solution using Cartesian direction vector. The image vector for the point of interest is virtual -45, 48, and minus is to be 100, not minus. Please, we'll correct that. Okay, minus is for A when we are doing, the focal length is always used as negative when we are doing area photography, not close range photography where our camera is pointing horizontal. Now, so we compute our image coordinates, virtual one, -45, +48, and +100 mm. Now, the location of the camera, the location of the camera is in the survey coordinate system. We have to do a swapping of the camera coordinate where our Y will change to Z and our Z will change to Y. I explained to you before that when you are using your camera, the Z axis of the camera is the optical axis, and that is what we use for pointing. So the Y is pointing upward instead of Z. So Z and Y are interchanged. And for us to do a calculation, we have to interchange any ground information that we are bringing into the equation so that it will be in the correct orientation for calculation as we see. Now, first of all, permutate the position of the camera, which is given as 100 meter X, 0 meter Y, and 1.2 meter height. So we do a swapping of that coordinate because it's a ground information. Okay, so we swap it first, and we swap it by multiplying it by this permutation matrix. They call this one permutation matrix because it reorganizes your coordinate axis, and that permutation matrix is saying that it's an identity matrix where you change Y position to Z and you change Z position to Y. That's what is showing on the screen. This is X position, which is not affected, but Y is supposed to be 1 here. We move it to Z and move from Z, we move Z to Y. So we have interchanged X and Y. And when you use it to multiply the object location, it gives you a permutated object location in a left-handed coordinate system. So we can use it in this form for realizing that when we finish our calculation, it's always the object coordinate that we are going to get, and that object coordinate will not be correct until we have reversed permutation that we did. Okay, so we have a permutated object position P naught as A equals 100 meter X minus 1.2 meter Y and minus 0 Y, 0 Z. But we realize that even though we label it as XYZ, when we come back, we have to reverse the permutation that we have done. So you see the calculation. Now, the object space coordinates give us the small s, which we have computed before, and that's what you have. Now, the direction vector can be obtained by dividing that s, 119.704, this is to divide the actual image coordinates, the direction vector. Now, this information, which gives us this, the magnitude, we have broken that that segment matrix into magnitude and direction. So we have magnitude and direction. Okay, they have removed the negative here. That negative does not show here. Okay, so this is what we have. Okay, this is the correct direction of the line, and this is the correct magnitude of that line in the image space in millimeters. Okay, you have to take note of the unit because all the coordinates that we have here are in millimeter, but for the direction, these are direction cosines. That image space vector ST is what you have here. The scale S is 119.704 times the direction that we have. Now, generate the length of the object point ray using the formula given before, which we have as big S equal small s over f times d. D is measured in the field. So from the small s that we have measured, which is 119, and we have computed it, 119 on 704, f is 100, and d is measured as 50 is given actually. Not measured, d is given, but if you are not given, you have to measure or you have to measure, okay? So we get our d, and by multiplying the space S is 59.85 liters, okay? Because F and S are in the same unit, so they will cancel themselves, and then this thing will come out in the unit of meters. So our scale, the distance on the object is 59.852 meters. Now, the formula that we have for hence the position vector for the object is given as P equal P naught plus big S times T. And big S has been computed at 59.852. Okay, and the T is the same because the lines are collinear. In other words, the lines are along the same straight line, so they have the same direction. So this direction is used for this T bar in the object space. For the big S, we're going to use 59.85 as we have computed it from what we have. So when you multiply that into this direction, you get this unit, 77.05 meters in the X, 25.2 meters in the Y, and 50 in the Z. Now, when you do your calculation, you get a result. Now, this total, okay, is the totality of all of these. When you add this to this, what you get is 77.5 meters in X, 25.2 meters in Y, and 50 meters in Z. Now, the catch is this. These are the final result that we have gotten, but they are in object unit. But we know that we have permuted, we have interchanged X and Y. So when we are returning this result, Z must go to Y and Y must go to Z. So by a reverse permutation, which we see here, he said we must return. We must return the result to the coordinate system of the object by another permutation matrix, which is this one. So the exact same manipulation where we change Y for Z and Z for Y. You multiply this matrix by this, you get your correct object coordinate. So 77.5, 50.0, and 25.2. So what the question says is find the height of the point, and the height of the point is 25.2 meters above the ground. Does anybody have a question? Does anybody have a question?
No, sir.
Is very clear? Is it very clear?
Yes, I think so, sir.
Okay. Now, I give you a take-home example to work. Take-home assignment, although it's in the lecture notes, so you are going to get it. Now, this question says a single image was taken of the front face of the hotel in Lagos with a camera whose focal length is 100 mm. The image of a corner point on the hotel has image coordinates -45 plus 48. Given that the camera was located on a table at 50 meters from the hotel, compute the ground coordinate of the corner point. The camera position at the time of imaging is given as 200,000 meters easting, 320,000 meters northing, and 30 meters height. So compute the coordinate of the corner point. Okay, so do that and then submit as part of your assignment, class assignment. Now, I want to end this lecture. Well, I think somebody tried to solve that problem that I gave you, but I'm not sure it's correct. I'm not sure it's correct. So, but we are supposed to also treat, we have finished the treatment of single image method. What is left is to take the picture and follow the procedure in the lecture material. We can do that. We're supposed to treat the two imaging solution also. But because of the time that we have, I will just show you what the two image solution is and how we are not going to bother with that for now. Now, let me see whether we have image of a I want to see so many repetitions.
Some of these troops did come in with the troops that were some of them were troops that were already any additional troops going as you noted, we were still in the process.
Okay. Now, this is two image close range work. And the situation of the two image, let me see whether there's a picture.
Even though they had thrown in with the Leo, these are headquarters staff personnel, maintainers, some other enabling forces, either that completed their mission. Time and space are clean. So I want to push you back on the fact that when the president announced it, we hadn't pushed some buttons. We still have the Managed I have one of the
Okay. We are having the problem approach. You have two camera locations sighting the same object. Now the idea is shown on this page. So you can see me. You can still see me. The idea is that you now have, instead of a single image, you now have double image. One image on the left, one on the right, all pointing to a single point. So the same equation that we wrote for one, we have to write for two, and then find the method of solving the equation simultaneously so that they can give us the single object point, because the two rays are pointing to the same object point. So it must give us one solution. So we try to now optimize the two sites to get a better, more accurate, and that's the idea, which we try to which we try to give you. And I think we may not be able to find that immediately. I thought I saw, let me just see. Our time is up, but let me just see whether I have it at all. It's supposed to be another lecture note. Let's see what we have.
Thank you for doing this, John. Yesterday, the president mentioned to create contingency plans in case a number of American. Can you just explain kind of what
Okay.
the department is thinking about what its options might be to continue to get
Now, see an example of the two image CRP. You have one camera located at the left side, another camera located at the right side, and they are taking the picture of this same object. Now, by using the same equation, every point has at least two rays converging there. Every point of this object has two rays, one from the left, one from the right, and they all converge at that point. So those two rays will form equations for each one of them, and then try to solve them in an optimal way. Not in the approximate method of single image, but in the rigorous form, we solve that method. And the method is also explained here. Yeah, this is another view. You have an image on the left and an image on the right. They're citing different points. This is an object point, this is another object point. And then you can do your calculation. When you form an equation for example, from this camera, you form an equation for this line and an equation for this line. The two of them will be solved simultaneously to get the data estimate of this point. So two image solution provides more accurate result. We can even have a three image solution. You can have many image solutions, and then this gives us an opportunity to solve the problem simultaneously, and then gives us a very accurate result. Okay, so but we do not have time to complete it, and no question will come in the exam for 2 image solutions. But the question that will come in the exam for 2 image solutions will be asking you what is the advantage of the 2 image solutions over a single image solution. And I'm repeating it to you now that the advantage is that you have more accurate result and can use more mathematically refined method to solve the problem. A single image is an approximation which has no way of cross-checking errors. There's no way of cross-checking errors because only one measurement that you have per point. Okay, 2 solutions are better than one. Okay, just like you have 2 eyes to see, the only one eye you don't have accurate sight. So your accurate sight must 2 sides that are working very well. So that's the answer that you give if such a question comes to the exam. And you can see a building here, one image on the left, one on the right, citing the building. So you can measure coordinate on one photo, measure on the other one, generate your equation, form your solution, and the solution is going to be better than single image solution. Does anybody have a question on that? We also have procedure for 2 image solutions included in this something, or whether we should add it to what you have. Okay, there are calculations that are actually done there, but this is more elaborate than the previous one. We're supposed to study this question that involves some differentiation and all that, and then we'll form solutions with work examples. Okay. Well, I think you can study that later. We can give you these 2 solutions as part of what you have, the material you have. It is more elaborate than really quite elaborate. It's okay. Does anybody have a question before we close the class? Does anybody have a question?
No, sir. No, sir. No question from here, sir.
Okay. I gave you an assignment which is in the note, so you have to see and solve the problem and submit. Then,
okay, sir.
When can your lab would also be included, but the lab will just simply be that you go around, take picture, and then measure some coordinates on the image, and then try to do some calculations and submit. But that will be detailed in the material you are getting. Okay. When can we have our test? Or we substitute a lab and the take-home assignment?
Yes, I think so, because we did a lab for 504 already where we took pictures and submitted a report of 3,000 words. So we submitted that for 504 already.
Okay, so this one will be that you do the assignment that I gave you in the class, the calculation assignment.
Yes, sir. Then we submit.
And then the which other one?
You gave us one question yesterday too as well, sir.
Okay, I gave you a question yesterday.
Yes, sir.
Okay, so submit your proper submission and then prepare for your exam. But if there is any need for the view lecture, don't hesitate to call me back. Is that clear?
Yes, sir, that's very clear, sir. Thank you so much,
okay.
Sir.
Okay, good afternoon, everyone.
All right, sir.
Bye-bye. Lecture is over.
Yes, sir. Thank you, sir.
Good afternoon, sir. Thanks, sir.
Okay.
Yeah, no, sir. I'm coming to your office now, but
It's okay. Yeah.
the people from your in have already logged on.
They already logged on.
Yes, sir.
Okay. So we'll see now.
Yes, sir.
Alter the today's flow, including the need to have protection for these moves.